Hello again, and welcome to our lecture on vectors. Some quantities, like time and temperature and, say, area, involve only magnitude. But yet in science and mathematics and engineering, there are other quantities that have both a magnitude and a direction. For instance, velocity. Not only is there a magnitude to the velocity, faster versus slower, but there's a direction. Which way are you pointing? Acceleration has both magnitude and direction. Force. In engineering, force is not only the certain magnitude of the force, but in which direction are you applying the force? And those are different. So vectors are used to describe this situation where you have a quantity that has both magnitude and direction. And the way you represent that is with a so-called directed line segment. It'll have an initial point and a terminal point and an arrow joining them. Let me add that vectors are used a whole lot in calculus, but especially in second and third semester calculus courses. In the advanced placement program, vectors are used just a little bit, and of course in physics and science courses they're used all the time. So let's talk about the setup for vectors. Imagine a point P and a point Q joined by a directed line segment. P will be called the initial point, Q the terminal point, and we indicate that by an arrow on that directed line segment showing the direction from P to Q. A very common notation for this is the set of letters PQ with an arrow on top to indicate that it's a vector. These vectors have length, and in a minute we'll calculate the length of some vectors, and that's usually denoted by two vertical lines around the vector PQ. That said, in many textbooks that notation is different. Sometimes it's just single vertical lines, like the absolute value symbol. So please check your textbook or the manual that you're reading in order to be sure about the notation. We say that two directed line segments having the same length and the same direction, we call them equivalent. Let me show you a picture of some equivalent directed line segments. Loosely speaking, we'll say that all of these vectors are the same vector. They all represent the same vector. So you can kind of move vectors around as long as you preserve their length and their direction. More technically speaking, the set of all directed line segments that are equivalent to a given one, that's called the vector V in the plane. But loosely speaking, we'll just say we can move vectors around as long as we preserve direction and magnitude. As I said, the notation for vectors can vary with different books. I like a little arrow over the letters PQ. Sometimes a vector will be denoted by a lowercase letter, sometimes boldface, like boldface V or boldface U. Again, the magnitude, a couple of vertical lines is the notation we'll use, but that's not uniform at all. So again, check your book that you're reading, your textbook, to make sure of the notation. Let's do an example. Let's talk about how to represent a given vector and verify, in fact, that two vectors are equivalent. So imagine the following scenario. The point P and the point Q are joined, where P is the origin 0, 0, and Q is the point 3, 2. And then consider another directed line segment joining R and S, where R is 1, 2, and S is 4, 4. Here's a picture of that situation. I have two directed line segments, one beginning at the origin and going out to 3, 2, and the other one begins at the point 1, 2 and ends at 4, 4. Now they kind of look equivalent in this picture, don't they? They look like they have the same length and the same direction. Let's actually prove that using some of our pre-calculus skills. To show they have the same length, we would find the distance between the endpoints. So the length of PQ would be 3 minus 0 squared plus 2 minus 0 squared, all square rooted. That's the Pythagorean theorem. And you get 9 plus 4, or the square root of 13. For RS, you would get, similarly, the square root of 4 minus 1 squared plus 4 minus 2 squared, all square rooted. Now, and that also gives the square root of 13. Okay, so they have the same length. What about the slopes of these two lines? They'd be pointing in the same direction if they had the same slopes. Well, remember what slope is. Change in y over change in x. So for PQ, the slope is 2 minus 0 over 3 minus 0, or 2/3. And the slope of RS turns out to be the same, 4 minus 2, difference in the y values, divided by 4 minus 1, again 2/3. So those directed line segments are equivalent. They represent the same vector. Now, one of those vectors in that picture, PQ, started at the origin. Its initial point was at the origin. We call that standard position. And if you're in standard position, then the terminal point determines uniquely that vector. And so the coordinates of that terminal point are very, very important. And you indicate that vector as, with brackets now, v1 comma v2. And that indicates the terminal point of a vector in standard position. Okay? v1 and v2 are the components of your vector in standard position. For instance, the origin, not a very interesting vector, its coordinates are 0, 0. It's the vector 0, 0. It has no length and no direction, really. In that previous example, the vector represented by PQ in standard position would be given by 3, 2, using brackets to indicate that it's a vector. By the way, that notation is also not consistent across all textbooks, but we'll use brackets to indicate that it's a vector. If we use parentheses, then it's the point 3, 2. But with these brackets, it's the vector 3, 2. Okay, so let's describe the technical definition now of the component form of a vector. If the initial point is P1, P2, and the terminal point is Q1, Q2, then the vector PQ is given by Q1 minus P1, comma, Q2 minus P2. That would be the component form of our vector V, joining those 2 points. And its length, its magnitude, using the vertical lines, would be nothing more than Q1 minus P1 squared plus Q2 minus P2 squared, all square rooted. All right, some more notation and definitions. If a vector is length 1, if its magnitude is 1, it's called a unit vector, and we'll be using unit vectors in a moment. And of course, a vector is the 0 vector if and only if its length is 0. That's kind of a nice way to show that a vector is the 0 vector. And I can't stress enough that in calculus and in physics and in engineering and in science, people deal with vectors all the time. In this lecture, we'll talk about vectors in the plane. We're talking about planar vectors, two-dimensional situation. But in real life, of course, we're living in 3 dimensions. And so there's a whole world of 3-dimensional vectors out there that is beyond the scope of these lectures. Let's illustrate some of these ideas with a quick example. Let's find the component form and the magnitude of the vector that it has initial point 4 minus 7 and terminal point minus 1, 5. Okay. Here I've drawn the situation. There's 4 minus 7 where the vector starts, and it finishes up at minus 1, 5. Well, here's how we go. P is 4 minus 7, and that's P1, P2. Q is minus 1, 5. That's Q1, Q2. So we subtract. V1 is Q1 minus P1, or minus 1 minus 4 minus 5. V2 is Q2 minus P2, 5 minus a minus 7, or 12. So in standard position, we have the component form minus 5, 12. Here's a picture of that. There's the original vector PQ, starting at 4 minus 7 and finishing at minus 1, 5. We've now constructed an equivalent vector, an equivalent directed line segment starting at the origin and going to minus 5, 12. That's the same vector. What's its length? Well, the Pythagorean theorem again, minus 5 squared plus 12 squared, that gives the square root of 169, which is a perfect square. That's a 13. All right. So kind of a nice picture, I think. You're given the beginning point and the end point, the initial point and the terminal point, and in a sense you kind of move the vector so that it begins at the origin. And then those coordinates minus 5, 12, the coordinates of the end point, of the terminal point, are the components of the vector. Okay. So where did all these vectors come from? Well, it has a long, complicated history. Let me just name three mathematicians that worked a lot in what we call vector calculus and the development of the theory of vectors. Hamilton, an Irish mathematician, Grassmann, the German mathematician, and the American Joshua Willard Gibbs all had a lot of input into developing vectors. Today, vectors play a role all over science, thanks in part to these three great mathematicians. Now, you can combine vectors. For instance, the sum of vectors or multiplying a vector by a real number. Let's do the definitions, and then I'll show you some examples. Suppose you have the vector u1 comma u2, and I'll denote that vector u. So u equals in component form u1 comma u2, and in a similar fashion v is v1 comma v2. How do you add them? U plus v, you add the components. Thank goodness, it's a pretty easy definition. u1 plus v1 comma u2 plus v2. How do you multiply them by a real number? Again, it's pretty simple. A real number times a vector is multiply the individual components by that real number. And by the way, in this business, they don't say multiply by a real number. They make things more complicated. They call that scalar multiplication. So you can multiply by a scalar, and that's a fancy way of saying multiply by a real number. So given a vector, or given two vectors, you can add them or you can multiply them by scalars. Here's a picture of what that scalar multiplication does to a vector. It's kind of a neat picture, I think. Here we've drawn a vector v in arbitrary position. It has a certain direction and a certain length, and then we've tried to indicate what 1/2 v would look like. Well, it would be the same direction. When you multiply by a scalar, you don't change the direction, you just change the magnitude, the length of the vector. So 1/2 v would be half as long, 2v would be twice as long. What about minus v? What would that look like? Well, that would multiply each component by -1, wouldn't it? It would reverse the vector. So minus v is the opposite direction of the original vector, and then we've also indicated what -3/2 v would look like. Let's do a specific example. Let's add and multiply some vectors here. So let's let v be -2, 5, w say be 3, 4. Let's play with these vectors. What would 2 times w be? Well, that would be 2 times 3, 4. That would be 2 times 3, comma, 2 times 4, or 6, 8. Notice that the components have been doubled. How about v plus 2w? Well, -2, 5, plus that answer we just got, 6, 8, that would be 4, 13. You add the first components together, -2 plus 6 is 4, and 5 plus 8 is 13. Let's do a few more computations. What would -6, 8 be? Well, that means -1 times the vector 6, 8. So the components get multiplied by -1, and you're left with -6, comma, -8. That vector is the opposite direction of 6, 8. What if you were to add those two vectors together? Add 6, 8 with that new vector, minus 6, minus 8. What do you get? Right, 0, 0. In a sense, we have an additive inverse here, don't we? We've added two vectors and obtained the 0 vector. Now here's a picture of some of these vectors kind of put together in an interesting way. Notice I've drawn the vector v starting at the origin and going out to the point minus 2, 5. Our original vector v was minus 2, 5, so in standard position it would look like that. Then we calculated the vector 2w. If you remember, that vector was 6, 8. Well, I've drawn that vector, but I've moved it off the origin. I don't have it in standard position. It's been displaced in a parallel fashion. The directed line segment going from the point minus 2, 5 up to 4, 13 is equivalent to 2w. Here you can check that real quick. Subtract the x-coordinates, you get 4 minus a minus 2, or 6, and the y-coordinates are 13 minus 5, or 8. 6, 8 was the vector 2w, wasn't it? So I've drawn v and 2w, and notice that 2w's initial point is placed at the terminal point of v. And this is the geometry of vector addition. v plus 2w is the resultant vector starting at the origin and ending up at the point 4, 13. Isn't that neat? So you can represent vector addition by these triangle diagrams. Okay, you be the teacher for a moment. Student comes up to you. Professor, given a vector v, how can I describe what minus 2v looks like? How can I describe that, teacher? How would you answer the student? Given a vector v, describe minus 2v. Well, I'd try to do it this way. First of all, I'd say the new vector is twice as long as the old vector because it's 2v, but there's a minus sign, so it's in the opposite direction. Twice as long, opposite direction. And then I'd show an example to the student. I think a lot of learning takes place when you show examples. For example, if v is the vector 1, 3, then minus 2 times v would be minus 2 times the vector 1, 3, which is minus 2 minus 6. And here's a picture of that. There's the vector 1, 3, and then the vector minus 2 minus 6. You see that it looks a lot longer, and it's in the opposite direction. All right, good. I think we're comfortable with adding vectors, multiplying them by a scalar. Let's now move to something called unit vectors. And this will play a big role in the rest of this lecture and next lecture as well. Imagine the vector minus 6 minus 8. Okay, the vector minus 6 minus 8. It's not a unit vector. And by unit vector, I mean a vector of length 1. It's not length 1. In fact, what is the length of that vector? Well, let's do the usual trick. Its magnitude, its length, is minus 6 squared plus minus 8 squared, all square rooted, 36 plus 64, square root of 100, or 10. So that vector is length 10. Now, can you think of a vector in the same direction as v, as the original vector, but having not length 10, but length 1? I want to shrink it down to length 1. How could I do that? Right. Take the vector and multiply it by 1/10, or divide it by 10. That will shrink it down to a unit vector. So 1/10 of the vector minus 6 minus 8 is, if you bring the 1/10 inside, scalar multiplication, it's minus 3/5 comma minus 4/5. And that is a unit vector. The length of that vector is 1. You can just check it. Find the length of that vector, 9 over 25 plus 16 over 25. That adds up to 1. So given a vector, to construct a unit vector in the same direction is pretty simple. All you have to do is find the length of the original vector and divide by it. Okay. Now, there are two unit vectors that occur over and over. They're kind of obvious unit vectors. The vector 1, 0, that's nothing more than going out the x-axis 1 unit. That vector, a horizontal vector, is a unit vector. And the vector 0, 1, a vertical vector starting at the origin and going up the y-axis, 0, 1 is a unit vector. And they're so important, they're given special symbols. I, and this is a boldface I because it's a vector, equals the vector 1, 0, and j equals the vector 0, 1. If you were doing three-dimensional vectors, there'd be a third one called k in the third dimension, but we're only doing planar vectors. So I and j are our two sort of fundamental vectors. And watch what you can do with them. Take any old vector, you can write it in terms of these two special vectors. For instance, the vector -3, 8 would be -3 times 1, 0 plus 8 times 0, 1. Or, if you want to use our new symbols, -3i plus 8j. What we've done is we've expressed an arbitrary vector as a linear combination of I and j. Now, a little warning here. The symbol I that we're using for the vector 1, 0 should not at all be confused with the square root of -1. Remember, we had I equal the square root of -1 in the complex numbers. Those are completely different ideas. The boldface I is a vector in this lecture. Okay. I've mentioned about, of course, how important vectors are in calculus and engineering in describing motion, velocity and acceleration of particles. Vector operations are also very, very important in calculus. And in fact, these vector operations of addition and scalar multiplication are so important that over time, an entire course has been built up based on analyzing vectors. And it's called linear algebra or vector analysis. It's a subject that students usually take after calculus, and it deals with issues of what are called vector spaces. And a vector space consists of a set of vectors and those two operations we were talking about and a lot of properties that those operations satisfy. So if you're at a university, you might see in the catalog courses called linear algebra. They're talking about the kind of vectors that we've been developing today. Let's go on. Let's use these unit vectors now to talk about how to express an arbitrary vector in a very convenient form. Remember, I is the unit vector 1, 0, j is the unit vector 0, 1. Now I want to express direction. Okay, so here's a picture that will help me express the direction of a vector. Imagine a unit vector u making an angle theta with the positive x-axis, and the endpoints of this vector u will be xy. So what is x? Well, we go back to the original definition of trigonometry. X is cosine theta and y is sine theta. That's how we defined sine and cosine in trigonometry. So the vector u, which is a unit vector here because that circle was a unit circle, can be described as cosine theta comma sine theta, x comma y. It's really a convenient notation. It says that you pick an angle theta and you move out, and u is a unit vector in that direction theta. Theta is often called a direction angle, and u is the unit vector in that direction theta. Now, you can write this slightly differently, but more conveniently. Factor out the cosine theta, and you have cosine theta times the vector 1, 0 plus sine theta times the vector 0, 1, and that equals cosine theta I, where I is our new symbol, plus sine theta j. So that is a way of describing an arbitrary unit vector in terms of its angle. Well, now wait, suppose I had a vector that is not a unit vector, but length longer or shorter. Suppose the vector v has length v with vertical lines around it. You could describe that vector as follows: length of v times the corresponding unit vector. In other words, if v is a long vector, it's nothing more than the unit vector stretched out the appropriate length, and that length is the length of v. So with length of v times cosine theta comma sine theta, and then you can do the manipulations and get length of v times cosine theta I plus sine theta j, and that's often written as length of v times cosine theta I plus length of v sine theta j. That's a very standard way of describing a vector v. It has sort of two components to it, two issues. One is the angle theta. That's telling me the direction of my vector v. And then there's a multiplication by the length of v. That tells me the magnitude of v. It's a very nice form. Let's do a quick example of this new idea. Suppose v is the vector 3, 3, which would be 3i plus 3j. What's the length of the vector 3, 3? Well, it's 3 squared plus 3 squared, all square rooted. 9 plus 9 is 18. Square root of 18 is 3 square roots of 2. What angle does the vector 3, 3 make with the positive x-axis? Yeah, a 45-degree angle. So we can describe this vector v as length of v times cosine theta sine theta, or 3 square roots of 2 times cosine 45i plus sine 45j. Again, that's a very attractive way of describing this vector. It tells you the angle it makes, and it tells you how long it is, all in one simple equation. Here's a picture of our vector v making the 45-degree angle, and it ends up at 3, 3, and we described it using the length and the angle. Okay, good. Let's talk about some properties that unfortunately are not true. Let me ask you some questions about some things. For instance, is it true or not that the magnitude of the sum of two vectors is the sum of their magnitudes? In other words, if you have two vectors and you add them up and find out how long that is, what's the length of that sum, is that the same as the sum of the individual lengths? What do you think? Is the magnitude of a sum of two vectors the same as the sum of their magnitudes? Well, I claim it's false. Some of the good news about mathematics is when something is false, all you have to do is find a counterexample. Can we think of an example that shows that this is not true in general? Well, how about some of our simple vectors? What if we take the vector I, which is 1, 0, its length is 1, and the vector j, its length is also 1. I is along the x-axis, j is along the y-axis. Each is a unit vector. What about their sum? Well, their sum is 1, 0 plus 0, 1, or the vector 1, 1. And what's the length of the vector 1, 1? Well, that would be 1 squared plus 1 squared, all square rooted, or the square root of 2, which is not 1 plus 1. So we've shown a counterexample to this idea that the magnitude of a sum is not the sum of the magnitudes. Too bad, but it's just not true. It's another question for you. Given an arbitrary vector, how can you find a vector in the same direction, but of length 1? In other words, a unit vector in the same direction. Well, we've seen how to do this, I think, but let's formalize it. You're given a vector v. It's a long vector, say. It's not length 1 necessarily. And you'd like to have a vector in the same direction, but length 1. What do you do? Well, here's what I would do. I would find the length of v, and then I would divide v by its length, producing a new vector. That vector is in the same direction as v. It's just a scalar multiple of the vector. But this new vector, which I'll call u, turns out to be a unit vector. The length of u is now 1. How about a vector that's a unit vector but in the opposite direction? Right. Just take minus u, and that would be in the opposite direction of u. Okay, good going. We spent a lot of time on vectors, a full lecture on them. Not nearly enough time to talk about all the interesting properties of vectors. I invite you to look at and even a calculus book on vectors, because in many calculus books, the chapter on vectors doesn't use any calculus. It uses just the ideas that we started today. Next lecture, we're going to continue this study of vectors, and we're going to do a combination of some really interesting ideas. We're going to bring in our friends, the complex numbers, and we're going to see how ideas related to vectors can combine with complex numbers and trigonometry. And we'll be able to do things like this: find the cube roots of a number, the 3 cube roots of a number, even if those cube roots might be complex. And then I'll also show you next time, perhaps without derivation, one of the most beautiful and amazing formulas in mathematics. It's a formula that involves some of the most important constants in all of science and math. It involves pi, which we love since we took geometry, the number e, which we've seen in our study of logarithms and exponents, and the number I, square root of -1. Those 3 numbers are all inside the same formula. So I look forward to seeing you next time. Thank you.